So today we're going to start section 12.5. 12.5 is definitely the longest section in this chapter. There's going to be multiple videos to kind of walk you through the different types of problems, the different things that we're going to talk about. And 12.5 is where we're finally going to kind of put together a bunch of the different ideas that we've talked about in the other sections. So in this section, we're going to talk about sets of data that form bell-shaped distributions and learn how to determine the percentage of data that fall either below or above a particular data value in that set. So when we're looking and kind of thinking about where we started, at the beginning we started talking about some different definitions, and we started talking about distributions. So distributions of our data set. We talked about frequency distributions. So what we're going to do is we're going to take this idea of using a frequency distribution, and we want to talk about and we want to pay attention to three different things. So the first thing that we're going to look at is our measure of central tendency. Right? We talked about this in section 12.3. Right? And we talked about mean, median, mode, some different ways of talking about our measures of central tendency. In these particular examples that we're going to go through today, we are going to focus in this section on our mean. Right, in the last section we talked about measures of dispersion. Right? So we talked about range or standard deviation. We're going to use our standard deviation as we go through this section as our focus of dispersion or spread or variability. Right? So since we've already talked about these first two things for numerical distributions that we want to study, we're going to start by focusing on the last thing that's listed here, our shape. What does our distribution look like visually? All right, so when we're looking at distributions, we should look for basic characteristics. Right? Is the distribution bell-shaped, symmetric, or is it another shape? Again, we are going to focus on ones that are bell-shaped and symmetric as we continue on through this section, but we are going to talk about our other different shapes as well at the beginning, and how many mounds appear. Mounds are going to be related to our idea of mode that we saw back in section 12.3. Okay. All right, so this first image here that we have is a uniform, which is a type of a symmetric distribution. Right, so symmetric distribution means if we were to take this distribution, if we were to take this graph, right, and fold it in half, if we were to take our sheet of paper and fold it in half in the middle of our graph that way, right, we would have the same thing. We would have kind of mirror images on each side of our graph. Right? It's uniform because it doesn't change. Right? Sometimes this is also called a rectangular distribution because all of the observations occur about the same frequency, and our frequency distribution actually turns into a rectangle. Right, so this is a uniform and symmetric distribution. All right. The next type is J-shaped distributions. So in J-shaped distributions, the frequency is either constantly increasing or decreasing. Right? So if we were to draw the letter J on here and kind of connect our top to our bottom and shade it in, that's what we have. So a J-shaped distribution, we are either always increasing in this case or decreasing as in that case. Okay. This next example is an example of a bimodal distribution. So we did look at modes in section 12.3, and we said that modes were our values that showed up at the highest frequency. Looking at this distribution, we can clearly see that we have two values that are showing up at our highest frequency. So this is what we would call a bimodal distribution. The actual modes themselves don't need to be exactly the same. So notice that our bars aren't exactly the same height. They're close, but they must have a frequency that's greater than our other values in the distribution. All right. The next type of distribution that we're going to look at is we're going to look at a skewed distribution. So a skewed distribution has more of a tail on one side than the other. Notice that it's not the same as our J-shaped distribution, right? Because in our J-shaped distribution, we never go back down. But in this case, right, we see this, but then our curve falls. We see this increase, but then our curve falls going that way. So our skewed distributions are different than our J-shaped distributions because it's not constantly increasing or decreasing, right? There is a rise and fall on both sides. Right? We separate skewed distributions by talking about them about their tails. So the tail is the longer, skinnier part. So if we look at this first one has a tail, right, that's over on the right. This one has a tail that's over on the left. So a graph is skewed right if its tail is on the right side of the graph. A graph is skewed left if its tail is on the left side of the graph. And the tail referring to the part that has the, right, a lot of either decreasing or increasing values on this side, but we see kind of as we're looking at the curve more of a tail. And we can see that tail if we don't just look at our frequency histogram, but if we were to kind of sketch this out as a more rounded curve. So these longer pieces on either end, that's what we refer to as our tails. The relationship between mean, median, and mode are showed for skewed distributions. So based on what type of distribution that we have, in a distribution that's skewed to the right, our mean is larger than our median, and which is larger than our mode. And then if we go the other way, if it's skewed to the left, well then they go in the opposite direction. The mean is the smallest, the median is larger than that, and then the mode is the largest. All right, so all of these different types of distributions can be used and are studied commonly in statistics, but we're going to focus on this last type. We are going to focus on a bell-shaped symmetric distribution. All right, so it is symmetric in the same way that our uniform one was at the beginning. Right, symmetric if we fold this in half. If we take this sheet of paper and fold this in half, right, bringing those two edges to the middle, we're going to have something that's very similarly shaped on both sides. Thinking about the idea of tails, right? Our tails are pretty equal on both sides. It's also called bell-shaped because if we were to draw kind of a rounded curve, right, we would kind of go up and then down in something that's similar to the shape of a bell. The highest part is in the middle, right, and our tails are on the left and right side. All right, in our next example, or in our first example, I should say, we're going to look at some different data sets and identify what type of distribution shape would we expect from this. Right, so college GPA from a random sample of students. So if we were to think about this, we would hope that a large sample of students would have a larger GPA. Right? So that means thinking about this, we might see a tail on the left and then see a larger number of high GPAs coming from our college students. Right? So if we see this tail on the left, right, remember then we're going to call it a left skewed distribution. Right? We have more high GPAs, which causes a tail on the left side, on the lower side. A symmetric group of SAT scores from a random sample of students. In this case, we would be looking at something that is more bell-shaped and symmetric. Right. Most of the students are going to be near the middle or average. Right. So we're going to have a large portion in the center, right? There's our peak, there's our mode, and then small tails on either side, so it is more bell-shaped symmetric curve. The last digit of Social Security numbers from a random sample of adults. This one we would expect to be uniform, which is also another type of symmetric distribution. Right? Our distribution is random and pretty even. Income from a random sample of adults. Well, unlike our college GPAs in our first example, our income, right, we're probably going to see more adults that have a lower income and less that have a larger income. So we're going to see a peak kind of on this side and a long tail on our other side. So this would be an example of a right skewed set of data. Right? We have more lower income. Right? So we're going to see our tail then on the right. And then our last example, data were collected on the finishing times of 2 different marathons. One marathon consisted of elite runners from the 2012 Olympic Games, while the other marathon included amateur runners. What would we expect our distribution of this sample to have? Okay. So here we're going to see a peak for our Olympic runners, which is going to be shorter than a peak for our other runners. Right? So this would be an example of something that could possibly be a bimodal distribution. Right? We see one mode for each group. Right. Once we get through our discussion of our different types of distributions, we are going to focus in this section on our normal distribution. Okay. So our normal distribution . Our normal distribution, or sometimes it's referred to as a Gaussian distribution, named after a mathematician, is one of the most important. It's what we're going to use again for the rest of the section. Many sets of data are normally distributed. The graph of a normal distribution is called a normal curve. Right? And the key thing that we're looking at here, the normal curve is a bell-shaped unimodal, so we have one mode in the middle, and symmetric about the mean. Okay? So what we have here is a nice bell-shaped curve. Why do we like using normal curves? Because our mean, median, and mode of a normal distribution should all be at the center. They should all be approximately the same value, if not exactly the same value. Right? It's also worth noting that normal curves with smaller standard deviations are taller and are more narrow. They have less spread. And normal curves with larger standard deviations are shorter and wider. They have more spread. So if we look at this last example down here at the bottom of this page, right, what we see here, if we were to draw kind of an invisible line going through the middle, notice that both of these images have kind of the same center point, right? If we were to fold them in half here, they would be symmetric about the same point. So since their middle is the same, that means that they have the same mean. But notice that one of these is much taller, right? The one that's much taller has a smaller standard deviation. The one that's shorter and wider has a larger standard deviation. So they have very different standard deviations in this example. Right. Now if we compare this to the example below here, where our center point, notice for the women and the men, is different. So our point where they are symmetric is different, but they are relatively the same height and the same shape. So in this case, they would have these same standard deviations, but they would have different means, right? Different center points that they're symmetric about, but our shape and height are the same. In the next video, we're going to look a little bit more closely at our normal distribution.